Well, good evening, everyone. Welcome to Environmental Coffee House, and I am your cult leader, Sandy Schoelles.
And I am your cult leader adjacent, Jennifer Hynes.
Hi, Jennifer. How are you?
I'm
How are
good,
you, honey?
Sandy. How are you doing today?
Well, been working hard on this one. And I just
Yeah.
want to say hi to everyone in the chat really quickly, like I usually do. Robert and Kim, thank you for moderating. And Scott, thank you for moderating. And El Slayer and Looney Tunes and Bila and Hans, thank you very much, Hans, by the way. And Trulia and everybody else, thank you for being here. Now, Jennifer, would you like to
Mhm.
give the 10,000 feet overview of our show?
Absolutely. So, guys, after a wonderful slideshow that Sandy has assembled, all about methane, we're all about methane. We're going to take a quick look at the entry in Wikipedia, actually, about the last glacial maximum. We're going to talk a little bit about the last glacial maximum and what it means to us today. And then we're going to run over to the conversation. Rising methane could be a sign that Earth's climate is part way through a termination level transition.
Ooh.
Sandy, that sounds scary.
Yeah. Well, I think it is when you learn about
Yeah,
what we're going to teach you if you don't know about it already.
that's right.
That's
That's
right.
right.
All
And then we're
right.
going to run over to phys.org. Also starts with research shows. Different article though. Research shows shrinking Arctic glaciers are unearthing a new source of methane. Very, very interesting. And if we have time, we'll have to see. We're going to talk about this very interesting article from the New York Times. Worms revived after 46,000 years, frozen in Siberian permafrost. Oh dear.
Oh boy.
Zombie worms.
They're not worms. I didn't have a worm sound. All right. So here we
All
go.
right.
Here we go. I'm going to put us on here. All right, guys. So here is our presentation for tonight. And we are going to start with this. Here we go. Let's hope it's wait. Oh, for God's sakes. Hang on a second, guys. This happens with this stupid software every single freaking time. All right, the system audio should be okay now. Sorry, guys. Shit happens.
These diverse sources add to the challenge of tracking this potent greenhouse gas. A molecule of methane is able to trap more heat than a CO2 molecule. In fact, it is the second leading gas that is contributing to climate change. And since the Industrial Revolution, global methane concentrations have doubled.
It's contributed roughly 20 to 30% of the climate change that we've experienced to date. And so there's an urgency in understanding where the sources are coming from so that we can be better prepared to mitigate methane emissions where there are opportunities to do so.
By using a combination of field observations, airborne surveys, and data from international partners, NASA has been able to create a new model of the sources and global transport of methane. This model allows scientists to track the global methane budget and better understand the changes over time.
Everything around methane tends to be a few years behind carbon dioxide, so we're just catching up to how important and how dynamic methane is as a greenhouse gas. We see these pulses of methane in different places, and when we look deeper, we understand that those pulses are occurring for different reasons. So we might see wetlands in one region, we might see industrial pollution in another area.
With this new model, we can track the pulses of methane across the globe to better pinpoint the conditions and activities that may cause them.
Methane is a difficult gas for us to understand given the diversity of sources and then how the sources and the emissions get transported throughout the atmosphere. The 3D simulation that we produced here helps us better put together the entire story for the sources of methane and as well as its removal from the atmosphere.
By taking a look at the story of methane, scientists and policymakers can better understand the sources of methane emissions and work to reduce this greenhouse gas.
All right.
Wow. Oh, yes.
Scientists.
That's right.
Oh, the scientists.
Okay, Sandy, I'm going to go ahead and read this one. So, guys, a model comparison shows that recent changes, methane's rapid growth since 2016, may be comparable or greater in scale and speed than methane's growth and isotopic shift during past glacial, interglacial termination events. It remains possible that methane's current growth is within the range of Holocene variability, but it is also possible that methane's recent growth and isotopic shift may indicate a large scale reorganization of the natural climate and biosphere is underway.
Wow.
And that is from Ewan Nesbitt et al.
Oh, yeah. He's the
Methane.
big guy. He's the big guy, the writer of a lot of this. Yes. So here's the planet and thawed permafrost. There we are. What a mess.
As our planet, Earth, continues to warm, we're seeing a shift in weather patterns around the world. Glaciers are melting and sea levels are rising.
In Siberia, this summer had record-breaking temperatures of more than 100 degrees. The hot weather caused the permafrost to start to thaw, causing volcanic-like bursts. Meteorologist Sean Stiles explains in this Earth 8 report.
We are coming off of one of the hottest summers I personally can ever remember, temperatures well over 100. But when you think of the Arctic Circle, you definitely don't think of temperatures over 100. But this year, they had plenty of them.
It goes to the place like a volcano where it gets to be so much gas that explodes.
Geologist Dr. Pat Abbott is referring to the methane bursts that have been occurring in Siberia.
In areas inside the Arctic Circle, they had high temperatures over 100 degrees. Never had to happen before in history.
That heat has started to thaw the permafrost, the frozen layer of Earth below the topsoil.
As temperatures go up and ice starts melting, that means ancient vegetation is now decaying, bacteria are eating it, and you're releasing methane, carbon dioxide, all the gases that come along with decomposition of organic material.
Typically, these gases escape, but because of the extreme temperatures, they build up quick.
But in some of these areas of Siberia, the gas is trapped beneath enough of that ice that you literally get an explosion, just like a volcanic explosion.
Abbott says these craters can be huge.
The size of some of these things are amazing, like 165 feet across, like 160 feet deep. So it should be like the depth of a 16-story building. In other words, we're talking massive eruptions.
He says these bursts have happened in the past, but are now being accelerated because of the heat.
There's over 7,000 of them that have been identified in Siberia, and over 400 of them are looked at as being in imminent danger of eruption. Good news, though, none of them are near a city or a town.
So as more of these methane bursts occur, they will release more greenhouse gases into the atmosphere.
As the Earth warms, it causes more things to cause more warming, and you get this cascading effect where one thing leads to another. Warmth only going to continue to grow in amount and magnitude over time.
So as we heard from Dr. Pat Abbott, as long as these above average temperatures into the 100s continue, we can expect to see more methane bursts in Siberia.
Well, we have talked on this show. How many shows, Jennifer, have we done on methane and permafrost and all?
A lot. I would
Yes.
say maybe even 50%
Yeah.
of our shows. I mean, maybe.
lot of
You
them.
know, we've studied it a long time. I've studied this a long time as well, probably
Oh, yeah, you have.
well over a decade. So
And so a lot of this leads to this.
ooh.
Now just watch.
Glacial River.
Look at that. Going,
Oh.
gone.
Oh.
Yeah, I'll show it one more time. Thank you, Scott Duncan. Going, gone, guys. Gone.
Oh.
Yeah.
Ooh.
So there you go. Jen?
Yeah, so interesting, guys. So, what we're looking at here is a little bit of a historic overview. And I'm going to get to my one here so I can look at it. So, the last glacial maximum, that's LGM. So, we've got a couple of different measurements here for the last glacial maximum. How it was like 21,000 years ago was the last glacial maximum. So you can see anything that is shaded was like from that time period, and you can also see how the coast has changed. It's so interesting because what you can see here, especially if you look at that kind of olive green swatch right through like where Alaska is, and also kind of out where the Kara Sea is, all of that white just below. So that is basically where the land extent was at one point. And in the last glacial maximum, sea level was at least 100 meters less than today. And all that was highly vegetated or whatever land. I mean, and then the ocean moved in, and so we are interglacial right now. And all of that has turned into a distillation, these methane hydrates and cathrates. So the highest, kind of pure methane, just pure energy. So what is happening now is as the ice continues to pull back and all of that, what used to be land, is warmed, and these are extreme methane deposits. Also, take a look right there above the green where all those little dots are. Those are the age of the permafrost. And what you can see here is that the darkest dot, so let's like black color, is the most ancient permafrost, and that is between 650,000 years ago to 2 million years ago. So take a look at that. That freaking permafrost that is black has been there since the beginning of time, as far as we're concerned anyway. So it's very interesting. This area, of course, is under great change right now, and as the planet continues to warm, it's only going to get it's going to change faster, and the methane is definitely going to come out. I mean, methane hydrate plus heat equals methane in the air, and methane goes straight from the hydrate state, say that 5 times fast, into the gaseous state instantaneously. So it goes from hydrate to gas with the addition of heat. Where could all this heat come from? From our atmosphere, from the oceans that are taking up all that heat. So there you go, guys. It's happening on a planet near you, and that's kind of the drill down of it. That's it.
Happening on a planet near you. I like
That's
it, Jen.
right. That's
Well,
right.
next we're going to move on to one of our favorites. It's kind of a maybe not about methane, but it's an overview, and I thought you guys would like it.
Might have seen this headline today or yesterday that this past month of July, which just ended a couple days ago, was the hottest month ever recorded, globally average temperature on Earth. And it's likely it's also the hottest month in at least 100,000 years. Last interglacial we had was about 8,000 years ago. And ever since that time, the Earth had been getting cooler up until present day. And what we see that starting in about the 1950s or so, the Earth wasn't getting cooler anymore. In fact, it was getting warmer at an incredibly rapid pace. So this says now at 1.1 degrees Celsius, warmer than it was before we started using the atmosphere as a dumpster, basically, for our waste products from burning fossil fuels. Today, actually, this month, it's closer to 1.5 degrees Celsius warmer than it was back then. So already we're seeing a really dramatic shift. And if we keep going the way we are and not reducing our emissions of what we call greenhouse gases or heat trapping gases, which include carbon dioxide and methane, we're going to continue to warm so that by the end of this century, we'll be somewhere up around 4 or even 5 degrees warmer than we are right now. And we know that those greenhouse gases, especially carbon dioxide and methane, trap a lot of heat in the climate system. Global warming is not happening evenly around the globe, but this is an interesting way to show it, I think, because it's not just showing you the warming, it's showing you the warming relative to the globe as a whole. And so these blue areas here, over the oceans mainly, are where it's warming slower than the globe as a whole. And the red areas, which are mainly over land, are where it's warming faster than the globe as a whole. And what you see is that up in the Arctic here is where it's warming the fastest of all. In fact, now the Arctic is warming about 4 times faster than the globe as a whole. And this has some really serious implications. One of them is that we're losing the ice that's floating on the Arctic Ocean. This animation is showing you how the thickness of that ice has been changing over time, going back to the late 1970s. So just to get you oriented, here's Greenland here. This is Scandinavia. This would be Siberia and Alaska over on this side. These colors are showing you the thickness of the ice, where the yellows and white colors are where the ice is very thick. And then where it's blue, it's where it's much thinner. And so as we march through time, what you notice is that in the early years, there's a lot more of the whites and yellows. And as we get to the present day, those whites and yellows are basically gone. Most of the thick ice has disappeared from the Arctic.
Jennifer Francis will be our guest in October. That's what
We can't wait.
We can't wait. Let's hope it works, because she told me October. But we're going to move on. And we're moving on to this. Metric ton per year as of 2021 by Frank Mitlower. And he talks about the anthropogenic sources and the magnitude. And it's interesting because coal mining, oil and gas industry, landfill and waste, ruminants, rice cultivation, biomass burning, industry, biofuels, transport. So the total anthropogenic. And then what did he leave out, Jennifer?
Well, this is a look at anthropogenic sources of methane. So now I do understand it. But there are a lot of other sources of methane other than the ones that we make. So we're looking at this and it's like, okay, we are making this. We can control the methane somehow since we're making this, and these are different sources. What we don't see is the non-anthropogenic ones, which would include the wetlands, rice paddies, things like that, and Arctic methane, which is definitely coming into play more. We shall see how it goes with the Arctic methane as it gets hotter and hotter in the Arctic. Those methane hydrates are going to start to thaw out and go directly into the atmosphere, which creates instantaneous heat, because over a 10-year time period, methane is like 80 times molecule for molecule stronger than carbon dioxide as a greenhouse gas effect. So there you go.
Then we're going to move on. This was last year. And of course, it's we always have to show Professor Elliot Jacobson something from Elliot.
Right. So what is interesting about this? This is not the global methane levels. This has nothing to do with global methane levels. This is what is being added annually. So this is kind of the rate of add of global methane to the atmosphere. And, we all understand patterns. And if we look back, and I think that's around 2005 for our global rate of add since that time period, so that's the last 20 years, right, guys? It's just going up. If you even out, for the highs and the lows, you get a pretty good polynomial trend line right there. It has that bend in it, which is what you're always looking at when you analyze data. You want to see, is it flat? Like, oh, that's flat. That's flat. There we go. Or is it curved? And if it's curved, there's some level of increase, whether you want to call it, people tend to get a little hung up over the terms exponential. Is it exponential or not?
Right.
I don't know, but the thing is it curved or not? Is it a polynomial trend line or not? And if it is got a curve in it, that means by definition that more is being added than before. And that's kind of what we see here since the last 20 years.
Now we'll segue a little bit to research. And don't take the perm out of permafrost. The young researchers are so sweet and they are so earnest in what they're doing. They totally really care, and there are quite a few projects. I picked this one. This is in Subpolar Project. Our team is installing custom chambers to measure methane and carbon dioxide emissions resulting from permafrost degradation, a significant step in understanding the impact of climate change on polar ecosystems. And we know all the studying in the world won't stop it in the melt and the leaks, but provide information and data for scientists and us, Yeah. So I give them so much credit, for everything that they are doing. And yay. Thank you to all the young researchers, and there's a lot of them, and that's a good thing. Now, this is a shocking discovery. Bubbling methane craters and super seeps grow all along the East Siberian and Arctic ocean shelf with concentrations of atmospheric methane 15 times above the planetary average of 1.185. Look at that bubbling stuff.
Oh boy.
I think this was from Just Collapse. Look at it. I know I have that sound. I have that sound somewhere. I didn't set up the bubbling sound.
Yeah, that methane seep. Gosh.
Look at it. And this is seriously happening in many different spaces, in many different places. Wow. Just look at it. Now we're going to move on to Peter Carter. Peter Carter has done a ton of work on a lot of this, and you guys, you should be familiar. He's been our guest. He's all over. He's with, what's the name of their channel? Well, Paul's with him. Paul Beckwith is with him, and oh my God, it just. You guys know. If you know what the name, put it in the chat, because all of a sudden I had a brain fart. So he started talking 2020. This was the science of methane feedback runaway. And I'm just going to go down here. In summary, the complex and nonlinear processes governing the sources and atmospheric chemistry of CH4 cause a feedback loop. And the feedback loop can be described in simple terms as rising CH4 emissions, wetlands, thawing permafrost, and destabilizing marine hydrates, which is increasing the CH4 concentration amplified by the effect of CH4 on its own chemical lifetime, results in greater radiative forcing on climate and terrestrial ecosystems. So finally, the resulting additional radiative forcing could lead to more or faster thawing of permafrost, further destabilization of marine hydrates, and potentially even larger wetlands emissions. Comment, Jen?
Well, I think that's a pretty good summary of the methane feedback runaway thing, which we all fully expect to happen. You look at everything and you look at the methane stores and the amount of methane hydrate that is resident all through the Arctic. And you just know when the Arctic sea ice goes, the temperature of the Arctic Ocean is going to increase. And I mean, like we said before, heat plus methane hydrate equals methane in the atmosphere, and we know how potent it is, and we know that there's an extreme amount, and we know that the deposits are real. They are not fake news. They are true methane hydrate deposits laced throughout the Laptev Sea, the East Siberian Arctic shelf, especially in the Kara Sea, Sweden, and coming out of rocks. And what even more than the biologic source of methane, which is, of course, notable, right? We've been talking about that, is the geologic source of methane, which is becoming more understood and more evident. We're going to talk a little bit more about this in a bit.
Yeah.
But yeah, this is, it is what it is, guys.
And I'm going to move on because this is pretty comprehensive. So this is from Professor Juan Nisbet, and he is like the guy. I mean, he's really the guy on all this study. So the methane emergency. Methane's meteoric rise in atmosphere, mainly wetlands and mainly tropical. Climate change, which I don't like the word anymore. It's global warming, it's climate emergency, climate crisis. Climate change makes it easy for people to just say, well, the climate always changes. I can't stand it. Okay. Methane in the air has just passed 1,900. This is 2022 parts per billion. That's a fire alarm. Before human industrialization, it was about 700 parts per billion. Now it is rising fast. Is this caused by increased human energy use, gas leaks and coal mining, or are new feedbacks happening with warming feeding more warming? Methane's important. Its warming impact on global surface air temperature is about 0.6 degrees Celsius since the year 1750, according to the new Intergovernmental Panel on Climate Change report. That's roughly half carbon dioxide's impact. Methane grew strongly in the 80s. Then it stabilized. In 2007, it began to rise again, led from the tropics and subtropics, and at times the high north, with the strongest growth on record in 2020. Methane's lifetime in the air is 9.1 years. It comes from natural sources, like 40%, like swamps, human activity, such as leaks of natural gas, which is mostly methane. Very roughly 600 million tons are emitted annually. Wetlands emit perhaps 200 million tons, cattle 115 million, landfills 70 million, fires 30 million, which may have changed. We've had so many more fires, Jen. Don't know.
Oh my God. Yeah.
Fossil fuel emissions from the gas, coal, and oil industries produce about 120 million tons annually, which we will see shortly. Rotting vegetation in wetlands and peat bogs makes methane both in the tropics, especially the Amazon, Nile, and Congo basins, and in Siberia and Canada, where beavers are magnificent methane machines, creating wetland and filling it with cut vegetation. So those little boogers are causing a little bit of...
We could just go on from there. I think we had one of those shows one time.
Yeah, we did. We had the beaver show already. Right. So the stomachs of... You have to laugh. Yeah. The stomachs of ruminants such as cows, sheep, and deer are microbiologically like wetlands. So these animals breathe out methane. Other biologically made or biogenic sources include landfills, sewage, and leaky biodigester facilities. Pyrogenic sources are crop waste, grasslands, forest fires, mostly human-lit. A clue to why methane has been rising since 2007 comes from carbon's isotopes. Carbon has two unradioactive stable forms or isotopes, carbon 12 and carbon 13, and radioactive carbon 14. Different methane sources have characteristic stable isotopic signatures. The radio of the carbon 12 to 13. Methane from fossil fuels and fires has significantly more carbon 13, while biogenic methane has slightly less. Ice cores show that for 2 centuries, up to 2007, the carbon 13 in the atmosphere methane was increasing, driven by fossil fuel emissions. But since 2007, when methane's rise was renewed, now lovely, the isotopic trend has reversed, now trending towards carbon 12. Very interesting science. That suggests biologically made emissions are driving recent growth past 2007. Why might biological emissions from wetlands and farming be rising, especially in the tropics where growth has been fastest and also in the high north? Wetland emissions increase with rising temperature. Rainfall, too, has increased recently in important parts of the moist tropics, both increasing wetlands and also supporting more grass and more cows, sheep, and goats. Goats. So could methane feedbacks be at work? And warming feeding more warming? Is there a methane emergency? Yes.
Yes. The answer is yes. The answer is yes. So interesting, Sandy. This methane feedback emissions from Siberia permafrost and subsea floor methane hydrate in the Kara Sea. So the first thing that looked like, if you look at the little map on the bottom, the long one, look at Sweden. That is like huge. Sweden is like so red. There's so much methane coming out of Sweden. It's, notable, and then of course getting into Siberia. I would have expected to see more in Siberia, so I'm not really sure why that is not the case. But I think they're doing permafrost and sub-sea floor methane hydrate in the Kara Sea. So most of this looks to be land measurement, but it is interesting. Some of it's going into the Arctic. You can see it kind of stretching in there. But I do believe that as time goes on, we're going to see, like, if you look at that one over in the upper right, like where Greenland's all white, see, the even more right, there we go. See how it's like all green right above the word Arctic and stuff like that? You would expect to see methane emissions. That's this East Siberian Arctic Sea, and right next to it where the M is basically in methane, that right there, that a little bit further up than that is the Laptev Sea. That's it. So you've got the East Siberian Sea and the Laptev Sea. That was all above water in the last glacial maximum. So let's wait and see what happens there. So very interesting.
And thank you, Peter. I know he's not watching, but thank you. And take it away, Jen, on Sam Carana's.
Oh yeah.
Newest.
Well, methane is nothing if not volatile, guys. And the thing is about methane, it's very bouncy, it's very jumpy, and it's a lot more volatile than the carbon emissions that we're used to seeing. And what you look for is patterns in the overall, which is easy to see, and patterns in the peaks and the frequency of the peaks. And the peaks portend the future, right? We know that basically they kind of portend the future. It's where we're going, at some point. So look at these measurements most lately. And this is real time. This is August. So we knew that it was bad all through June, right? That was when the North Sea measurements came out that were so high, right? And that was in June. Then we knew it was bad in July. Now look at the effect in August after basically some pretty brutal heat. Look at this thing. I mean, just look at it. There's nothing like it. There's nothing like it for the last 4 years. That's it. You know?
Wow. That's intense.
It is. Totally intense.
Totally. But this has been going on for years.
Barring any late season surges, we can now say that Arctic sea ice reached its peak extent for this year's freeze cycle on February 25th. It's the smallest winter maximum coverage since we began consistently tracking the ice pack with satellites in 1979, and the second earliest peak as well. Much of the winter ice pack consists of thin ice that will melt in the summer, and scientists say that while this winter did set a new record, trends in the summer minimum extent are more interesting scientifically and a better indicator of climate change. Here we see in yellow where the ice extent is low near the coast of Russia and Alaska, or more precisely, the difference between this year's ice pack and the average maximum coverage from the last 35 years.
Earth right now, but then. Yeah, and then, ooh. There it is from Copernicus.
So this is methane floating through the air at a certain altitude, is it?
Yes. And it just it's just a graphic that kind of stuns you. It's stunning.
Does.
It's really stunning.
Right.
But this is measured by satellite. You know, Copernicus looking at the atmosphere. It monitors all of this stuff. And wow.
Yeah.
Wow. Notice how Australia is a little bit cleaner. It's wild. It is wild. It is wild. Okay. It's all true. But ponder this. Is it too late?
A gas leak from a Pennsylvania storage field released 1 billion cubic feet of planet-warming methane. That's enough greenhouse gases to erase the climate benefits of half the electric vehicles sold in the U.S. last year. There's nothing natural about natural gas. It's a climate disaster. Gas leaks constantly, from fracking wells, pipelines, and even from the stoves in our homes. It's time to power our communities with clean electricity, not polluting methane gas. Follow Gas Leaks to learn more.
Okay, so follow Gas Leaks to learn more. That's sad. We'll do it again. Yeah. And here's an interesting one. Thomas Reese, who we follow on X, who's in the little group of ours. Jennifer, you're in it. Is this an attempt to reduce methane from ponds on a warming world? The hell is it? Look at that. We'll play it one more time. What are they doing?
I think they're trying to reduce the pond scum.
I don't know, but Thomas put it up.
They're trying to take the algae out of the water. It
He
looks
may
like it's
have,
an algae
and he
cleaner.
may have been being a little humorous on X, on Twitter, but I thought I would put it in there because, you know, I mean, seriously, yeah, you're probably right, but his words were, "Is it an attempt to reduce methane?" And I thought it was worth putting in, so there you go. So LNG methane terminals are a public health hazard. These facilities literally poison the communities they operate in, like Freeport, Texas, leading to several health impacts like asthma, heart disease, and cancers. And look at this. That's what it looks like.
It's freaking wafting through the atmosphere. Wafting through the atmosphere. We're just, I mean, we shouldn't really be surprised that this is happening to our Earth. This is like what we do. This is what we do.
It's what we do.
This is what we do.
And here's the Environmental Defense Fund. Good old Texas, huh?
Good old Texas.
And now we go from Texas to the UN, and of course they have their own report. We're not going to show you the whole thing, obviously, but they have a report called an Eye on Methane, International Methane Emissions Observatory 2022 report. I will put the link in the show notes
It's
if
good
anybody.
they're watching it.
Oh yeah, absolutely, and you know, if you're interested. So now we're going to move on a little bit, and we're going to move on to a little political. Living in denial, and this is Romsdorf, one of our favorites. Living in denial of established facts is a recipe for failure, if not disaster. For politicians, it's inexcusable. Whether humans are causing climate change and worsening the consequences of extreme weather events is not a matter of belief. It is a scientific fact endorsed by the climate science community, learned societies, and every government around the world. And we're going to move on because this is Howard Zinn. Jennifer, did you want to read this one, or do you want me to read it?
Oh, I can get to it very quickly. Howard Zinn. Come to me, Howard Zinn. Here he is. Okay, here we go, guys. Howard Zinn. Civil disobedience is not our problem. Our problem is civil obedience. Our problem is that people all over the world have obeyed the dictates of leaders, and millions have been killed because of this obedience. Our problem is that people are obedient all over the world in the face of poverty, starvation, stupidity, war, cruelty. Our problem is that people are obedient while the jails are full of petty thieves, and the grand thieves are running the country. That's our problem.
I would say he's amazing.
He is.
And now we're going to move on because I found a new guy to share with Jennifer, and we're going to look at him a lot closer. But Jen, want to read this one too?
Oh, yeah, sure. Okay. So, time to break the addiction to fossil fuels. Methane is a super potent greenhouse gas. At least 25% of today's warming across the planet is driven by methane from human actions. And this is Mustafa Santiago Ali who said that.
Yeah, and again, I just found him, and I'm going to check him out a lot closer. It's a slow apocalypse, but you'll work through it. This message has been brought to you by the government. Oh, my goodness. Oh. We had to throw a little politics in there, didn't we? Yeah, we definitely did. Oh, gosh. $20.53. I don't know. Okay, moving on. This is from the article, but Jen, go for it.
Yeah, so here we go from basically 1985 to the present. You can just see the methane emissions. And the thing to notice is that it's going steadily up. Again, remember we said this in the other graph, since about 2004. We saw some bumpiness in that other one. And then in 2004, things seem to be happening around that time period. And we are off to the races. We've got further acceleration. We've got growth of acceleration itself each year, and there we are. What to be said? We're going up, 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 up,
up and away, and it's not in a balloon.
My beautiful balloon.
My beautiful balloon. But see, we're showing our age, but we definitely are going up in like everything.
That's right.
All right. Now we're going to move on to what actually the topic. An interglacial period, or alternatively interglaciation, is a geological interval of warmer global average temperature lasting thousands of years that separate consecutive glacial periods within an ice age. The current Holocene interglacial began at the end of the Pleistocene about 11,700 years ago.
That's true. Yeah, it certainly did. And that was what we call the end of the last ice age. There was a little dip, a little cold dip right before that, probably from about 12,800 years ago to 11,700 years ago, which is about a 1200. There was a little, and then after that, we were out of the ice age and melting fast. So
Yeah, we are melting
go.
fast. Definitely. All right, so to give you a definition of termination, as used by quaternary geologists, oceanographers, and paleoclimatologists, is the period of time during a glacial cycle for when there is a relatively rapid transition from full glacial climates to full interglacial climates. For the quaternary period, terminations are numbered using Roman numerals from the most recent termination as 1, and with the increasing value, example 2, 3, and so forth into the past. So when I was reading the scientific material, I really had to learn it pretty quick because I was not familiar, and it's pretty interesting. Well, it's very interesting. I mean, it's fascinating. So, so this is what we will be talking about. Atmospheric methane's current growth has strong similarities to ice core methane records during glacial, interglacial termination events, marking global reorganizations of the planetary climate system. And that was Doug Sweden on X. And I have to tell you a funny story. I did all kinds of research on termination events. And you know what I came up with, Jennifer?
What?
So many things in human resources. And I was a human resources director professional and I had to handle those things. And it was like, well, wait a minute. This is not what I'm looking for. I know all about those kind of terminations. I did not know about, the interglacial terminations.
Right.
So,
Right.
which I found that was quite humorous for me, but
and
all
we're
right.
talking about the termination of an age. So this is basically the termination of the Holocene. Make of it what you will.
Yeah. All right. Well, we're almost finished with our this, but what I wanted to show you was, if those of you who are not familiar with Margot's Healing Corner on YouTube, she does a comprehensive methane, sea ice, and climate weekly roundup, and she does a phenomenal job. And she spends time and she does research. She does her research. I mean, she is phenomenal. And it's a shout out to Margot. Thank you for doing what so many other people don't. And she does a great job. So just in case you don't know who she is, I wanted to introduce you to her. So next we are going to look at these, and Jennifer, this is yours. Take it away.
We're just going to do a quick gander of the last glacial maximum, the pictures in Wikipedia, and we're going to go through them sequentially pretty quickly. So this is basically how the world looked in the last glacial maximum. If you look, you'll notice that England is not on this because it's part of Europe, right? And we also see that Australia is connected to New Guinea. And we also see that the whole down to Indonesia from Thailand, that Sundaland is in evidence. This is a very small picture, but we'll have another one. But it's just interesting to know, what did the coastlines of Earth look like when the sea level was 100 meters lower than today? So that's kind of why we're looking.
Yep.
Next. And this basically shows, this is a little bit strange picture to understand because the present is over on the left and the past is over on the right. But what you can see is we're coming out of, these are different temperatures for different measurements there. But the thing is to notice there are three lines that are all having roughly the same pattern. And that pattern is for the last 10,000 years, that right, like over on the left hand side, that first quarter of the graph that's very flat, that's been our rock solid climate the last 10,000 years. And it's going to get much more variable because we're dropping out of this pattern now. Yeah. And then this is just the maximum, the vegetation and where it lived and the types of it. Sandy, anything you want to say about this one?
No, I thought it was interesting, though. You can see all the different types of, boreal wild woodlands and savannas and grasslands. Very interesting graph if you want to spend the time. It'll be in, you can watch it. And the note that we'll put the link in if you'd like to look at it.
Absolutely.
Oh,
Okay, so
Jennifer loves
this,
this
I
one.
find this so interesting, guys. So a lot of people don't know about Sundaland and Sahul. So at the end of the last ice age, we are looking at the coastlines of approximately maybe, actually, this was at the maximum. This was at the glacial maximum. So this was roughly 21,000 years ago. Okay. So look at, like, where Thailand is. You take the S and you go straight up to that land mass above the S of Sunda, right? You go up, 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 up. That right there, Cambodia, Vietnam, Laos, Thailand, that's what we call Southeast Asia today. This land used to be much, much bigger, and it was called Sundaland. And there was more land lost from Sundaland, which was prosperous. It was full of humans, by the way. 21,000 years ago was a good time to be over in Sundaland. The climate was perfect. It was lush. It was fertile. They had, I'm sure, villages throughout. Ancient pyramids, in case have been discovered throughout Indonesia, right? Some of you may know about this, going back further than expected. And Sundaland was a place of civilization, and I myself am fascinated by Sundaland, and I want to know more about it. So I've bought whatever books I've been able to find about it. Also, take a look at this Sahul, right? This is the joining of Tasmania, Australia, New Guinea. It all was one big clump when the sea level was 100 meters lower than today. So I just find this is interesting. This is how the coastline used to look 21,000 years ago. So interesting. 21,000 years ago. And humanity, just to, not to drill on this point again, but humanity is more ancient than expected. And there were advanced civilizations, I am convinced, throughout Sundaland. So that's something to kind of study a little bit.
For a future show. Absolutely. Perhaps a guest. Yeah. Oh, you like this one too.
Oh, I do.
I do.
I do. So the green, the lighter green, that is the coastline of how it looked throughout Europe and the Mediterranean. And you'll see that Italy is joined to Sicily. You'll see that Ireland and the UK, England and Ireland are not, individual little islands. They are all clumped in with Europe. And it's a different world. There's the Black Sea is considerably smaller. The margins of the Mediterranean are, as expected, smaller. And it was a different world. Also to note, if this is the last glacial maximum, you would have had, if we go back 30,000 years, that was the end of the Neanderthal civilizations, or maybe civilization is the wrong word, but the Neanderthal
Time.
Time, right. And they were all throughout Southern Europe, France, Spain, and Southern Europe. And modern man was very, very active since 50,000 years throughout Europe, Southern Europe especially. So very interesting to see what's going on here, right?
Absolutely.
So interesting. Oh, so interesting again. What we can see here is basically the glaciers as they were. Look how low the glaciers extended over North America. Canada was 100% glaciated, and it was connected to Greenland because it was all glacial. And where you lived, Sandy, it was glaciated, wasn't it?
Yeah.
That's
And
right.
yeah, and there's things that actually I have found in my creek that may date back all the way. Who knows?
Oh,
I
yeah,
don't know. I really don't
definitely,
know. I just collect the
definitely.
stuff.
Beautiful,
Hmm.
beautiful. So this is kind of like the glaciers and how they looked, and I think it's fascinating.
It is
Yeah.
fascinating.
You can also
Completely.
I'll just say you can see the Himalayas, right? The Himalayas over by India. You can see the Swiss Alps over above north of Italy there. Yeah. So very interesting glaciers that existed in the
And look at the
past.
North Pole. Hmm.
So
Hmm.
interesting, right?
Very
Wow.
interesting.
Wow.
All right. And last but not
Yeah. So
least,
again, it's always, I love geography so much. It's so interesting. So this is the geography, the coast, a better look, better representation of the coastlines of 21 million, or excuse me, 21,000 years ago. And you can see, how Florida is kind of stubby because it's flat and it was bigger, right? And everything that we talked about, Sundaland, Sahul, everything's looking somewhat different than it looks today. All that saltwater intrusion that we see today along the east coast of the United States, um, that's all due to, it didn't exist back 21,000 years ago. Just didn't. So we think it's very beautiful, and it is, but it's all due to rising seas.
pretty wild.
Pretty wild.
Pretty wild. And guess what? Now we're
What?
going to move on to the pièce de résistance
Oh.
from the conversation. And I
Ooh.
think you'll read this one, Jad.
Okay, very good. Rising methane could be a sign that Earth's climate is partway through a termination level transition.
And that's why we wanted to tell you what it was.
Exactly. Since 2006, the amount of heat trapping methane in Earth's atmosphere has been rising fast. And unlike the rise of carbon dioxide, methane's recent increase seems to be driven by biological emissions, not the burning of fossil fuels. This might be just ordinary variability, a result of natural climate cycles such as El Nino, or it may signal that a great transition in Earth's climate has begun. Molecule for molecule, methane is much more potent greenhouse gas than CO2, but it lasts slightly less than a decade in the atmosphere compared to the centuries for CO2. Methane emissions threaten humanity's ability to limit warming to relatively safe levels. Even more troubling, the rate at which methane is increasing in the atmosphere has accelerated recently. Something like this has happened before. Sudden surges in methane mark the transitions from cold ice ages to warm interglacial climates. Methane was about zero point 0.7 parts per million in the air before humans began burning fossil fuels. Now it is over 1.9 parts per million and rising fast. Roughly three-fifths of emissions come from fossil fuel use, farming, landfills, and waste. The remainder comes from natural sources, especially vegetation rotting in tropical and northern wetlands. Methane is both a driver and a messenger of climate change. We don't know why it is now rising so rapidly, but the pattern of growth since the late 2006 resembles how methane behaved during the great flips in Earth's climate in the distant past. The methane record 2006 to present. In late 2006, atmospheric methane unexpectedly began rising. Methane had risen fast in the 19th and 20th centuries, but plateaued by the end of the 1990s. This rise was driven by fossil fuel emissions, especially from gas fields and coal mines. Imagine accelerating a car with your foot flat down. The car speeds up, but eventually, air resistance equals engine power, and the car hits maximum speed. 1999, it looked like methane had reached a similar equilibrium between its source and sinks. Then, in late 2006, the amount of methane in the air climbed fast. Even more unexpectedly, 5 years later, the growth rate sped up again. During the 2020s, the growth rate has become yet faster than even during the peak of the gas industry leaks in the 1980s. So here's a really good representation, and you can see what they're saying if you just take a look up to 1990 to 2006. It's a little bit bumpy and it tends to kind of even out, and then we're off to the races, as we discussed. Today's growth seems to be driven by new emissions from wetlands, especially near the equator, but perhaps also from Canada. Beavers are methane factories, which pull huge amounts of plant matter into ponds they've made, and Siberia. This is a result of climate change. Increasing rainfall has made wetlands wetter and bigger, while rising temperatures have boosted plant growth, providing more decomposing matter and so more methane. Emissions from huge cattle lots in tropical Africa, India, and Brazil may also be rising, and rotting waste in landfills near the megacities like Delhi are important sources too. Climate terminations. In the past few million years, Earth's climate has flipped repeatedly between long, cold glacial periods with ice sheets covering northern Europe and Canada, and short, warm interglacials. When each ice age ended, Earth's surface warmed by as much as several degrees centigrade over a few millennia. Recorded in air bubbles in ice cores, sharply rising methane concentrations are the bellwethers of these great climate warming events. With each flip from glacial to an interglacial climate, there have been sudden, sharp rises in the atmospheric methane, likely from expanding tropical wetlands. These great climate flips that ended with each ice age are known as terminations. Each has a Roman numeral ranging from termination 9IX, which happened about 800,000 years ago, to termination IA, which initiated the modern climate less than 12,000 years ago. For example, around 131,000 years ago, during termination 2, that was the last ice age before the previous one, the British climate suddenly flipped from glaciers in the Cotswold to hippopotami wallowing in what is now Trafalgar Square. Full terminations take thousands of years to complete, but many include a creeping onset of warming, then a very abrupt phase of extremely rapid climate change that can take a century or less, followed by a longer, slower period during which the great ice caps finally melt. In the abrupt phase of the great change that brought about the modern climate, Greenland's temperature rose by about 10 degrees C within a few decades. During these abrupt phases, methane climbs very steeply indeed. Is something dramatic underway? Methane fluctuated widely in pre-industrial times, but its increasingly rapid growth since 2006 is comparable with records of methane from the early years of phases of past termination events, like the one that warmed Greenland so dramatically less than 12,000 years ago. There is already a lot of evidence that the climate is shifting. The Atlantic Ocean currents are slowing. Tropical weather regions are expanding. The far north and south are warming fast. Ocean heat is breaking records, and extreme weather is becoming routine. In glacial terminations, the entire climate system reorganizes. In the past, this took Earth out of stable ice age climates and into warm interglacials. But we are already in a warm interglacial. What comes next? It's hard to imagine. Loss of sea ice in the Arctic in summer, thinning or partial collapse of the ice caps in Greenland and West Antarctica, reorganization of the Atlantic Ocean currents, and the poleward expansion of tropical weather circulation patterns. The consequences, both for the biosphere in general and food production in the South and East Asia and parts of Africa in particular, would be very significant. There is more to be done that could hastily stop methane's rise. Plugging leaks in the oil and gas industry, covering landfills with soil, reducing crop waste burning. Shooting the methane messenger won't stop climate change, which is primarily driven by CO2 emissions, but it will help. Roman numeral 921 denote past great climate transitions. There is no Roman numeral 0, but then any future termination scale transition will be different. A temperature step from our present interglacial climate to some new future that is warmer yet. Methane signal is still unclear, but the question remains, has termination 0 begun?
Oh,
Dun, da, da, da.
That was good.
Dun, da, da, da.
Yeah. Well, we have one more, and it's been an hour and 11 minutes. So what do you think, Jen? Should we go on to the research shows shrinking Arctic glaciers are unearthing a new source of methane?
Yes, and then I guess we can save the worms for next week.
Okay.
How's that?
We'll save the worms. We had a little
Yes.
a little wormy, squirmy one, but
this one is very interesting, Sandy, before you begin, because it's going to talk about this brand new source of methane that is geologic in nature, and it's so fascinating and somewhat scary at the same time. So there you go.
All right.
I'm really a big fan of this article.
Okay. Well, as the Arctic warms, shrinking glaciers are exposing the bubbling groundwater springs, which could provide an underestimated source of potent greenhouse gas methane, finds new research in Nature Geoscience. The study, led by researchers from the University of Cambridge and the University Center in Svalbard, Norway, identified large stocks of methane gas leaking from groundwater springs unveiled by melting glaciers. The research suggests that these methane emissions will likely increase as Arctic glaciers retreat and more springs are exposed. This and other methane emissions from melting ice and frozen ground in the Arctic could exacerbate global warming. These springs are considerable and potentially growing source of methane emissions, one that has been missing from our estimations of the global methane budget until now, said Gabrielle Kleber, lead author of the research, who is from Cambridge Department of Earth Sciences. Scientists are concerned that additional methane emissions released by the Arctic thaw could ramp up human-induced global warming. The springs the researchers studied hadn't previously been recognized as a potential source source of methane emissions. Kleber spent nearly 3 years monitoring the water chemistry of more than 100 springs across Svalbard, where air temperatures are rising 2 times faster than the average for the Arctic. She likens Svalbard to the canary in the coal mine of global warming. Since it's warming faster than the rest of the Arctic, we could get a preview of the potential methane release that could happen at larger scales across the region. Look at that cave. Professor Andrew Hodson, co-author from University Center at Svalbard, said living in Svalbard exposes you to the front line of the Arctic climate change. I can't think of anything more stark than the sight of methane outgassing in the immediate forefield of a retreating glacier. Previously, research has centered on methane release from thawing permafrost, frozen ground. While the focus is often permafrost, this new finding tells us that there are other pathways for methane emissions, which could be even more significant in the global methane budget, says study co-author Professor Alexandra Turchin, also from Cambridge Department of Earth Sciences. Hodson added, until this work was conducted, we didn't understand the source and pathways of this gas because we were reading about studies from completely different parts of the Arctic where the glaciers are absent. The methane delivering springs they identified are fed by a plumbing system hidden beneath most glaciers, which taps into large groundwater reserves within the underlying sediments and surrounding bedrock. Once the glaciers melt and retreat, springs appear where this groundwater network punches through the surface. The researchers found that the methane emissions from glacial groundwater springs across Svalbard could exceed 2,000 tons over the course of a year, which equates to roughly 10% of the methane emissions resulting from Norway's annual oil and gas industry. This source of methane will likely become more significant as more springs are exposed, said Kleber. If global warming continues unchecked, then methane release from glacial groundwater springs will probably become more extensive. Glacial groundwater springs aren't always easy to recognize, so Kleber trained her eye to pick them out from the satellite images, zooming in on areas of land exposed by retreat of 78 glaciers across Svalbard. Kleber looked for the telltale blue trickles of ice where groundwater had leaked from the surface and frozen. She then traveled to each of these sites by snowmobile. I got to get rid of that. Hang on. Okay. By snowmobile to take on samples of groundwater at locations where the ice had blistered due to pressurized water and gas buildup. When Kleber and the team profiled the chemistry of the water feeding these springs, they found that all bar one of the sites studied were highly concentrated with dissolved methane, meaning that when the spring water reaches the surface, there's plenty of excess methane that can escape to the atmosphere. The researchers also identified local hotspots of methane emissions, which were closely related to the type of rock which the groundwater emerges. Certain rocks like shale and coal contain natural gases, including methane, produced by the breakdown of organic matter when the rocks formed. This methane can move upwards through fractures in the rock and into the groundwater. In Svalbard, we are beginning to understand the complex and cascading feedbacks triggered by glacial melt. It seems likely that there are more outcomes like this, which we have yet to uncover, said Kleber. The amount of methane leaking from the springs we measured will likely be dwarfed by the total volume of trapped gas lying below these glaciers, just waiting to escape, said Hodson. That means we urgently need to establish the risk of sudden increase in methane leakage because glaciers will only continue to retreat while we struggle to contain and curb climate change.
Mm. 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 And there you have it.
Wow. Pretty
Yeah.
heavy duty stuff.
Pretty heavy duty indeed.
Mm-hmm.
That is for sure.
Yeah, I'm looking at the comments. I hope you guys liked the show. There was a lot here, a lot to take in, a lot to learn, right?
Mm-hmm. There certainly was. And we'll continue to learn about methane. As you saw, most of those graphs only went back to 1985 when they really started to take measurements of methane and study it. So our history immediate of observational study is not too big. I mean, see 1985, that's 15 years, and 2023, so that's 23 years, so 33, like 40 some years, is the amount that we've been studying this methane. And during that 40 years of observational study, we've seen it accelerate as
Yeah.
we've talked
As
about
we've seen.
tonight. And
Yep. Well, everybody, thank you for coming. Don't forget, we have the Buy Me a Coffee. We are not a monetized channel on purpose, okay? Because how do you monetize doom? But if you'd like to help us, we have that fundraiser. And Jennifer, would you like to say something, bid adieu?
Well, I don't know. I mean, everything is interesting and horrifying all at the same time. And this is just, we're kind of doing drill downs into different areas of this climate disaster and taking a look at it as students of the apocalypse.
Students of the apocalypse. I like it. I like it. Well, yeah. Thank you. Thank you, everyone. And we'll see you next Friday. And actually, I said I wasn't coming back, but I do have a guest Tuesday night, and it's a surprise. And I also interviewed Margaret Klein Salomon, and I have that in the hopper. So we are busy. We are busy. Thank you, Jennifer. And
Thank you,
you know
Sandy.
what? You know how much I love you.
I love you too.
And you know what? We didn't do a flush of the day.
Ooh,
We never
let's
did a
flush
flush.
that methane away.
I'm just wondering. Yes, I think we need to flush. So there you go. We flushed the methane away. Yes, we did.